Okay? So the first thing is write a balanced equation between magnesium and oxygen. Okay? So the reaction for magnesium and oxygen. I've been told that writing balanced chemical equations is one of the things that people don't or struggle with. So we'll go through it slowly, step by step, and hopefully you'll become more confident in answering these questions. Okay, so this is the answer, but I'll go through how we actually got there in the first place. Firstly, the question is, what is the valence of magnesium? And the answer is 2+. Okay? It gives away 2 electrons to get stability. So its lost 2 electrons becomes positively charged by 2 charges. The valence of oxygen, it's an O, not an S, no, a 6. If you look on your periodic table, it's got 6 electrons in its outer shell, so it needs 2 more. And if it gets 2 electrons, it means that it's got 2 more electrons than protons. So it will be negatively charged by 2 charges, so it'll be -2. And so for every 1 magnesium atom, we can balance it with 1 oxygen atom, and then the net charge will be 0. See, if I put these 2 together, I get 0 out. Make sense so far? Now that we know that, we can easily write an equation. So we know that there's magnesium, and we know there's oxygen. So we have magnesium plus oxygen, and we know oxygen is O2, and we know it forms this substance here, because we know that when you put magnesium and oxygen together, you only need 1 of each. Now we balance, and it's quite simple. You got 2 oxygens on this side, 1 oxygen on this side, so what do? Well, I just multiply this side by 2. So now I've got 2 oxygens on this side, 2 oxygens on this side, and that balances. But now I've got 2 magnesiums on this side, and 1 magnesium on this side. All I have to do is multiply this one by 2. I've got 2 magnesium, 2 magnesium, 2 oxygen, 2 oxygen, so it's balanced up. If you look at our final answer, it's exactly the same. So what balancing equations requires is a knowledge of the valence of the things that are going in, and also a knowledge of the general form that we see certain chemicals in, like O2. That was just a trick that we happen to know. So when we look at pracs, we always have to look at certain aspects of it. We don't really look at the chemistry so much all the time. We look at other facets of it as well. So what is the major risk in this practical, and how can it be minimized? So what is the major risk? Burns from heating the crucible is the major risk. When you heat the crucible, it's getting really hot. That's a very strong hazard. So when handling the crucible, tongs should be used just to keep your hands away from the heat, to avoid accidental burns, and also letting the thing cool properly, not just being impatient and grabbing it, because that's a recipe for disaster. So that's how we minimize the risk. Tongs, and just ensure that we let things cool normally. We don't try to rush anything, because that's how accidents happen. So why is a crucible used as opposed to just simply heating the magnesium over an open flame? You put some magnesium in a Bunsen burner and you watched it brightly glow and then it disappeared. So why don't we just do that instead of using this silly crucible thing which doesn't show us the bright lights and things like that? Well, the crucible is used to ensure that the reaction is only between oxygen and magnesium. So we want to make sure that oxygen and magnesium is the only thing that's reacting. Within a Bunsen flame, several intermediate reactions could be occurring, so the final product may not be magnesium oxide, though it very likely is. When you have a flame actually has thousands of chemicals being produced and removed, and it's going on as the flame progresses. The flame actually has thousands of chemicals inside it, and any one of those could potentially ruin our experiment by bonding with the magnesium. And while it's not likely, it could actually happen, and that's why we want to try and minimize the error in this prac as much as possible. And that's why we use the crucible, to keep the flame away from the magnesium, and so we eliminate that error straight away. So again, simply to reduce error. Additionally, it allows all of the MgO to be collected compared to the direct heating case. If you've got a crucible and the magnesium's inside it and it becomes a powder, you've at least captured the powder. Whereas if you put the magnesium in the flame and the powder appears, it could go everywhere and you can't collect it. It just helps us practically like that. Keep in mind the crucible is also chemically inert because it's a ceramic, so it won't react with the magnesium. So what justification do we have to assume that the final product is magnesium oxide? Now that it's in the crucible, how do we know that it's magnesium oxide? I could just be telling you something that could be wrong. But there are lots of things that give us evidence that it is magnesium oxide. So the Mg is reacting with the air since the crucible is made of inert ceramic. So ceramics are very inert. They don't want to react with anything. We know that it's not going to be the ceramic that's interacting with the magnesium. Now the air is mostly composed of O2 and N2, and between these two chemicals, O2 is the most reactive because N2 has a triple bond. So N, there's actually 3 bonds between each nitrogen atom. And if you have to break 3 bonds, that's a lot of energy. We always want to go the easiest path. So oxygen will most likely react because the N2 is just so strongly bonded. Therefore, it's most likely that the oxygen will react with the magnesium, giving us confidence that the product will be MgO. So this is just evidence to prove that MgO is actually the product. So we eat the compound sodium chloride in our food, that's salt, and yet it's made from sodium, an element which reacts explosively with water, and chlorine, a greenish yellow gas, which is known to be extremely poisonous. Explain why we are able to ingest sodium chloride. So how come there's an explosive sodium and a poisonous chlorine, but when we put them together as sodium chloride, they're essential to our body functioning. So when sodium and chlorine combine to form sodium chloride, a new substance with different properties is formed. Now compounds have different properties to those of the elements used to make them. Compounds have different properties to the chemicals that they're made out of. Therefore, sodium chloride, which is soluble in water, doesn't react or explode, is composed of white crystals which aren't poisonous, and that's why we can ingest it, because their chemical properties have actually changed such that now, after reacting with each other, they've become completely safe to eat and actually important for us to survive. So that concludes today's lesson on the first-hand investigation for testing the properties of an element and its compounds. And so hopefully you've learned something about experimental technique as well as why we do certain experiments as well. So I look forward to seeing you at our next lesson.